Welcome all to part 2 of section 12.7. In this part, we are going to discuss a few special cases about acceleration, and then we will have a detailed example. Now, let's discuss some special cases. If we have a straight line motion, then t, which is equals to v dot, is going to be greater than 0 if the velocity is changing with time. But since this is a straight line motion, then an, which is equals to v square over rho, is going to be 0. And the reason why is that for a straight line, rho, which is the radius of curvature, goes to infinity. So you are dividing the velocity over a big infinite number, and this is why the normal acceleration goes to 0. And it is represented over here. So in this, as you move over a curve, you have tangential and normal acceleration. Over here, we have a normal and tangential acceleration. And once we move over a straight path, the total acceleration is actually only equals to at. It is not the sum of both because an vanishes. Now, on the other hand, if we have a motion over a curved path, but the speed is constant, in that case, we will have at, which is v dot, which is dv over dt, is going to be equals to 0, because we just said that it is a constant speed motion, while an is going to be v square over rho. If this, curve happens to be a circle like here, then basically rho is going to be the radius of this circle. But there is a velocity. Although it is constant, there is a velocity. And this is why you will get the total acceleration as an, because at is 0. So they will still have acceleration. Now, recalling that acceleration is defined as the change in velocity with respect to time, and since velocity is a vector, then it has both magnitude and direction. What is important here is that if we have a particle moving over a circular path with a constant velocity, then the tangential component at will be 0, because as we described before, dv over dt is equals to 0. However, you will still get a centripetal acceleration, and this centripetal acceleration can be thought of as a result of the change in the direction. So that acceleration is a result of the change in the direction, because as the body moves, although its tangential velocity is constant, but its direction is changing. That direction of velocity is changing, and the result of change in the direction of the velocity is the centripetal acceleration. We have 3 types of acceleration: linear, which is due to the change in the speed, even if there is no change in the direction. We have radial, which is also known as the centripetal, or sometimes we call it normal, which is a result of the change in the direction of the velocity, even though the velocity itself might be constant. We have angular, when the body speed and the direction are changing with time. So we call it angular acceleration if both of them are changing, both the magnitude as well as the direction. So let's have this example. When the skier reaches point A along the parabolic curve, over here in the figure, he has a speed of 6 meters per second. So his speed, VA, is 6 meters per second, which is increasing at 2 meters per second square. So this is basically the acceleration at this point. We want to determine the direction of his velocity and the direction and magnitude of his acceleration at this instant. Neglect the size of the skier in the calculation. Of course, because we are dealing with the kinematics of particles, not rigid body. Now let's start the solution. So we'll start with the velocity, and by definition, velocity is always tangent to the path. And since the path is given to us, which is y equal to 1 over 20 x squared, then we can take the derivative dy over dx, which is equal to 1 over 10x. And then we substitute dy over dx at x equals to 10. Why? Because here. So the position of point A is 10 meters from the origin right here. So clearly, if you substitute this dy over here at x equals to 10, so you put here 10 over 10, you will get 1. Which means that theta, which is equal to the tan inverse of dy over dx, is tan inverse of 1, which is equals to 45 degrees with respect to the x-axis. So from the x-axis, the velocity, which is equal to VA, which is equal to 6 meters per second, as given by the problem, is inclined at an angle of 45. So this angle from the x-axis is 45 degrees. Next is to find the acceleration. So the acceleration as a vector is equal to v dot ut plus v squared over rho un. Now, clearly, we need to know what is the curvature. So the curvature equation requires d2y over dx squared, which is from the previous relation going to be 1 over 10, because dy over dx was 1 over 10x, and x, here we take the second derivative, so we end up with constant. Now we write down the curvature equation. Rho is equal to 1 plus dy over dx square all to the power 3 over 2 divided by d2y over dx square, and the absolute value, and we will end up with 1 plus 1 over 10x, this is squared, all under over 3 over 2 divided by 1 over 10. Now we should substitute here x as 10 meter, and if we do so, we will get rho equals to 28.28. Now the acceleration then becomes a at a is equal to 2. Do you remember from the question? Was saying increasing at 2 meters per second squared. That was the acceleration at point A, and this one is the tangent component. So this is 2 ut plus 6, which is the velocity. This is 6 meter per second square divided by 28.28 meter un. And what we are going to get, we will get AA equals to 2 ut plus 1.273 un. And this is in meter per second square. Now, if we want to find the directions, we will do this in the next slide. But here, we can still find the direction of the component, because over here, this 2 meter per second square, which was given to us, which I said that it is tangent at point A, is already known. This is 2. So if this is the tangential component, it is not difficult to determine the normal component over here, which is in magnitude 1.273. And what is really unknown is this one. This is this component, the total component of the acceleration and its angle. And this is what we are going to do in the next slide. Now, let's calculate the total acceleration, which is A equals to the square root of 2 square plus 1.273 squared. Under the square root, this is going to give us 2.37 meter per second squared. Now, to find the direction, which is phi, the angle phi, shown over here, then we need to calculate it as the following. Phi equals to tan inverse of 2 divided by 1.273, which is going to give you 57.5 degrees. So let's look at this angle carefully on this diagram. Now, if you look carefully over here, I'm going to make the line fine so that I can draw. So this is the angle over here, and the opposite to the angle is this vector, which is basically equal to 2 meter per second. The adjacent side is this one. Now this one is 1.273. So this is why we say the tangent is the opposite divided by the adjacent, and then we calculated the angle. Now 57 is this angle. Now, how do we measure the angle with respect to the x-axis? The x-axis is here. That's the x-axis. And if you remember, this is how we calculated the angle 45 between the x-axis and point A in this. I'm talking about this point A. So what we actually need to measure is this angle. That's a small angle. So to measure this small angle, we have to say that 57.5 minus 45, that's degrees, is equal to 12.5 degrees. So that acceleration is equal to 2.37 meter per second square at an angle down 12.5 degrees from the x-axis. So in summary, we described a curvilinear motion using tangent normal coordinate system. We also defined the radius of curvature for general curve. We also talked about the velocity, the tangential, and centripetal acceleration. Thank you.